So let's take a look at the process of science. I said, when you guys see the red LO, number 1, number 2, etc., these are the learning outcomes for the course that I want you to make sure you guys are getting. That's the most important part of this entire course, is that at the end, you guys have a better feel for these learning outcomes. The goal is to increase your knowledge about each of these learning outcomes throughout the course of the semester. So these are things you'll be tested over repeatedly throughout the entire semester, and at the end of the semester, I'm going to try to measure how many of these learning outcomes have you guys mastered or gained throughout the time you spent in the course. Okay, so process of science. We're doing this all the time. We call it problem solving, troubleshooting, fixing things, etc. We pay our doctor a lot of money to problem solve when you go in and you're sick. You pay your mechanic a lot of money to do this process of science, and they problem solve and they analyze and they figure out what's going on. So when we're looking at science and biology, the knowledge we have is derived through this method. It's not just somebody's random idea or random thought. It's something that has been tested using the scientific method. Okay, so the first thing we do when we're looking at the process of science is we make an observation. My observation, my car won't start. Okay, I know it works. It worked before. It got me to school, it got me to work, got me to the grocery store, etc. And now my car won't work. So that's my observation. Once I have an observation, I'm going to formulate a hypothesis. Okay, this is an important term. Hypothesis. This is an idea. This is a guess. This is something you're thinking based on the observation. So I think my car won't start because I have a dead battery. That is a hypothesis. That is my guess. And what I'm going to do, now that I have a hypothesis, is I'm going to attempt to see if that is what the problem is. I'm going to problem solve this using the scientific method. Okay, so once I have my hypothesis, I then need to design and run an experiment to test my hypothesis. So one simple experiment. I think I got a dead battery. Now think about how many different experiments you could run to test your battery. You got a voltage meter, plug it in. That's one experiment. We can run that experiment. I can turn the lights on. Do I have lights? Does my radio work? That's a different experiment. I can try to jump it. Get somebody to come over with their truck or their vehicle, put the jumper cables on. There's a third experiment. I could pull my battery, take it down to AutoZone. Fourth experiment. You could design dozens of experiments to test the same hypothesis. That's what you do in science. You don't base this on one experiment to test the hypothesis. You design multiple experiments. The key is every experiment you design and every experiment you run, you record the steps, the methods, the details. How many milliliters of this? How many ounces of that? How long did you run the experiment for, etc. All those steps need to be listed out. It's like a recipe to bake cookies. You have to have precise information there. The ingredient list, the methodology, all that has to be there in the scientific experiment, in the scientific method. That way, it can be repeated. Okay, so I'm going to run my experiment. I turned my lights on. I got a jump. I used a voltage meter. And once I've run the experiment, I'm collecting data. Now, once I collect data, that's going to help me determine, am I right or am I wrong? Okay, so the data will tell me, is my battery dead or does my battery work? Sometimes it's a challenge though. We may get conflicting data. This meter says you have battery life. This meter says, or your lights don't come on. This says, no, I can't jump it. So collecting data is important. Lots of data is important. You don't base a decision on just one piece of data. You get lots and lots and lots and lots of data to be able to support or reject your hypothesis. Because once you collect the data, our next step is, do we support or reject the hypothesis? Now, most of the time, and this is why we pay mechanics and doctors and plumbers and computer programmers and all these different people a lot of money, is they can analyze this and they can take that data and say, okay, here's the problem. Now, most of the time in a realistic world, the data won't support the hypothesis. You go, it wasn't the battery. That's not why my car is dead. It wasn't the battery. The data doesn't support it. The battery's fine. The battery works. The lights come on. The meter says it's good. I didn't figure that out. So in the realistic world, you have a couple options here when your data doesn't support the hypothesis. I can redesign my experiment. I'm going to change experiment. I'm going to test it a different way. I'm going to do something a little bit different. I'm going to write down the steps, write down all the details, but I'm going to test it differently to see, do I need a different experiment? Will that different approach give me data that supports a hypothesis? It may not. It may reject. It may reject. It may reject. So at that point, you may say, well, I have data, but it doesn't support this hypothesis. Maybe I want to take the approach, I'm going to redesign the hypothesis. I'm going to come up with a new question. Here's a new idea based on the data. So, okay, the data supports or seems to suggest this idea. Let me redesign that hypothesis. Once you've redesigned the hypothesis, you retest. That's the key here. You're going to retest over and over and over with your new methods. Does that support your hypothesis? Does that support your idea? You're going to do this over and over and over. Once you have a significant amount of data, this isn't just one or two tests. This is dozens and dozens and hundreds and thousands of pieces of data to support the hypothesis. Lots of different folks have repeated it. Other scientists have done it over and over and over. Then we move to what we call a theory. In science, a theory is supported by data. It's a scientifically acceptable principle offered to explain phenomena. The key here is scientifically acceptable. The scientific world says this makes sense. All the data supports this. The experimentation supports this. All of these things support this idea. We now call it a theory. So things like the atomic theory. We have data to support this. Run experiments. And we have the atomic theory. The germ theory. This is what your doctor uses to figure out why you're sick, what to do to cure you, why we have a new flu vaccine coming out every year, how to cure and combat disease and illness and things that cause us to be sick. That's the germ theory. It's not a guess. Theory is not a guess in science. General usage, yeah, what's the theory about this, about the murder, about the crime, or about this or that? That's a guess. But in science, it's supported. It has fact, it has data, it has experimentation behind it. Theory of evolution. There is hundreds of years and thousands of pieces of data to support the theory of evolution. We continue to support it. We have more and more data every day that supports theory of evolution. So as we go through this semester, we're going to talk about these theories. Atomic theories, a little bit of chemistry we'll cover, germ theory, we'll talk about that when we talk about health and disease and our well-being, theory of evolution. We'll spend an entire unit on that, looking at the diversity of life due to evolutionary process. These are all things that are supported in the scientific community. There's data to back this up. They're not guesses. And often you'll hear people say that, well, I don't believe in this because it's just a guess. I don't believe theory of evolution because it's a guess, but I believe the germ theory. That's contradictory. You're believing one theory but not another because theory is a guess, so you're believing one guess but not. It doesn't work. You accept theory as fact, as data-supported scientific fact, or you don't. You don't get to pick and choose there. So we'll take a look at that as we go through the semester. But overall, here's our flow chart for the scientific method. This is how it's done. Observations based on previous data. You formulate your hypothesis. You run your experiments, or maybe it's observations. You collect data. That data draws you to conclusions. It may reject it. Then you come back and you start over again. Sometimes you're stuck in this perpetual loop here, over and over and over. Other times your conclusions are good, and then that is what helps us lead to calling something a theory. It's not lightly that the scientific community uses the word theory to say, here's the theory of. It doesn't happen quickly. It takes a lot of research and support and information and evidence to call something a theory. So make sure you guys are comfortable with these steps. Like I said, anytime you see those red LOs, let me zip back up and point it out again. When you see these red LOs, this is critical. This is something that you'll be tested over multiple times throughout the semester. So make sure you, at minimum, go over the material that covers those LOs. I'll be asking you questions on the quizzes and on the exams and in the labs that all point back towards those learning outcomes. All right, so again, keep in mind as we look at life, study life, we're studying it from a scientific perspective. We're looking at what can we test, what can we collect data on, and what can we support scientifically.